Hi everyone. Today we the students from second year EXCC branch from Sardar Patel Institute of Technology are here to demonstrate amplitude modulation and demodulation as a part of our mini project in signals and systems.
Hi everyone and welcome to the exciting world of radio waves. Today we are dividing into amplitude modulation or AM and frequency modulation or FM. These are two clear ways we use to send music, news and more through the air. We will learn how these techniques work and with the help of MATLAB, a powerful computer technology. We will even get to see them in action. Wonder how your radio turns into favorite station. It's all thanks to modulation. Uses sound itself can travel very far. To send it over long distance, we need radio waves. These are invisible waves of energy. Modulation is like attaching our sounds to these radio waves, kind of like hitching a ride in this adventure. We will use MATLAB or our guide. It's like our laboratory bench. We can experiment with AM and FM. So buckle up and get ready to explore the magic of modulation. And by the end, you will be able to say, I get it. Now let's talk about AM and FM. Imagine a flashlight. If you turn the light on and off, you are changing its amplitude. How bright or dim it is. That's similar to AM radio. We change the strength of radio wave to match the ups and downs of the sound signal. FM is a bit different. Think of a sound which has adjustable speed to change our sound. So instead of changing the wave strength or change how often it goes ups and downs. Before we get our hands dirty with code, we need to set up our MATLAB workspace first. Make sure you have a MATLAB installed. Think of it as installing a digital toolbox on your computer. Once you are in, we need to define some important parameters for a signal, like how long it should be and how fast it should play, which is sampling frequency. Think of it like setting up a music studio. Before you start recording, you need to adjust the microphone levels, right? We are doing something similar here with our digital signal. How to interpret and process our sound. Section 4. AM modulation in MATLAB. Now for the fun part, modulation. In MATLAB, we can use a simple equation to perform a modulation. Don't worry, it's not as scary as it sounds. This equation basically multiplies our sound signal with a special wave called a carrier wave. This is the wave that gets transmitted through the air. Imagine attaching a little note to a paper airplane and throwing it. This is something like a carrier wave. They travel together. Section 5. Demodulating the AM signal. Once our signal is modulated, we need to demodulate it on the receiving end. This process is like opening our note once the paper airplane arrives. We use another clever trick in MATLAB to separate our carrier wave, allowing us to hear the original message. It's like turning your radio to its right frequency. You are essentially stripping away the carrier wave and extracting the original sound information. So guys, let us know what is exactly AM modulation and demodulation. So first of all, AM modulation is a technique to transmit information like audio by varying the amplitude of the high frequency carrier wave based on the message signal. This helps send signal over long distances as the high frequency carrier can travel further. AM demodulation is the process of extracting the original message signal from the received AM wave, allowing devices like radio to play the transmitted audio. What are the real world uses of the AM? The first is the AM radio broadcasting, which transmits the music, news and talks shows over large areas. The second one is the two-way radios used in walkie-talkie and the CM radios for voice communication. The third one is the aviation communication, which enables the communication between pilots and air traffic control. The fourth one is the remote control, used in the older remote control systems and the devices like models. Why it's still used? AM is a simple, affordable and effective for long distance communication, though it's less communication. Now, what are the practical uses? So practical example of this is, think of a carrier wave as a steady light bulb and the message signal as a dimmer switch. When the song message gets louder, you turn up the brightness, and when it gets softer, you turn it down. The pattern of the brightness changes represents the song. So with the help of this pattern, we can get to know which song is this playing. What are the modern contexts? Why is AM less common today? The reasons are: because due to the better sound quality of the FM, due to the digital transmission, and the third one is the data transmission. Now, hereupon we can see the code of the AM modulation and demodulation. I will explain the code, and we will get to the output below. In this video, we are going to walk through a MATLAB code and demonstrate the amplitude modulation or AM, and how we can demonstrate the signal using the envelope detector to recover the original message. Now let's get started, guys. I will explain you the code in detail. I will also explain about the outputs which we get upon here. The first line is the FS 10,000. This is the frequency of the sampling frequency. The second one is the time interval. It is between 0 to 0.05, which is between the time interval 1 by Fs, which is given as 10,000. The third line is the F dash ms, which is 100. We have to take it as a frequency of the message signal in hertz. And the next is the F dash carrier. This is 1000, frequency of the carrier signal. All the command lines which are given here, F dash ms, F dash carrier, A dash carrier, this all will be new to you all. So we can go through the help desk and go to the documentation, find over that, and get the important command lines over. The next one is the A dash carrier. Here we are setting the amplitude of the carrier signal to 1. This is a constant amplitude that will carry out the message over a high frequency signal. The next one is the A dash ms equal to 0.5, and this line sets the amplitude of the message signal to 0.5. This signal is what we want to transmit. Next, carry upon the message signal, the sine wave. M dash equal to A dash message into cos of 2 into pi into F dash ms into t. This is the formula of the message signal. We should directly find that there is nothing another method to get this formula. So here we are defining the message signal, which is a simple cosine wave. The formula generates this wave where A dash ms controls the amplitude and F dash ms controls its frequency. The next one is the carrier signal. And now this line generates the carrier signal, which is also cosine wave, but as a much higher frequency, F dash carrier. The signal will act as a carrier for our message. The next is the AM modulation. With both the signals ready, we are going to modulate the carrier using the message signal. AM dash signal equal to 1 plus M dash t into C dash t. We can see over the code here. Here we are performing the actual amplitude modulation. To modulate, we multiply the carrier by 1 plus M dash t. By adding 1 to the message signal, we ensure the carrier amplitude varies in sync with the message, effectively encoding the message signal within the carrier. Now writing the code over here. Now we have to plot the message signal, carrier signal, and the modulated signal. Now let's go upon the subplot. What is the subplot 3, 1, 1 means? Here figure 1. 3, 1, 1 means there are 3 rows, 1 column, and this message signal goes upon the first box. Title message signal is written over here. We use subplot to create a plot for the message signal. Here we can see a simple way that represents the original signal. The second one is the plot of the carrier signal. Subplot 3, 1, 2, which is the 3 rows, 1 column, and the second figure, which is about the carrier signal. This plot shows the carrier signal, which has the higher frequency, as you can see in more frequent oscillations. The next graph is of the AM modulated signal. Finally, we plot the modulated signal. Here you will notice that the amplitude of the carrier wave changes to match the message signal. Next one is the AM demodulation using envelope detection. The code we used to write for this is AM dash demodulated Hilbert AM dash signal. This is the main code of the code. This is the main code of this project, as this line uses the Hilbert function to find the envelope of the AM signal. Taking the absolute value of this envelope gives us the original message signal back. Plotting the demodulated signal waves. Writing the code over here, we have to plot how the output is given. For finding the output, the command lines for the code are given below. Plot t, AM dash demodulated. I said upon that the AM dash demodulated is the main line of the code. The title of the code, AM demodulated signal envelope detector. As we can see in the plot, the envelope detector has done a good job of extracting the signal message from the AM signal. Okay, now explaining the output. We can find over that there are 3 columns. One column, three figures are there. Message signal. First one is the message signal of the top plot. This is the original message signal, a low frequency wave with an amplitude of 0.5. It's information we want to transmit. Second one is the carrier signal, middle point. This is the high frequency wave with an amplitude of 1, which will carry the message signal. Notice how it oscillates much faster than the message signal. The third one is the AM modulated signal, bottom plot. This plot shows the carrier signal after modulation. The amplitude of the carrier now varies according to the shape of the message signal, creating an envelope that matches the message wave. This is the combined signal that would be transmitted. The modulated signal combines the carrier and message, allowing the original signal to be transmitted over a high frequency. The next graph, the figure 2. The figure 2 is of the AM demodulated signal, the envelope detector. Using an envelope detector, after applying demodulation to the modulated signal, we recover a signal that closely resembles the original message signal. The peaks of the waveform follows the same pattern as the original low frequency message, which indicates successful recovery. The envelope detector extracts the varying amplitude of the modulated signal, allowing us to retrieve the information of the encoded by the message signal. And that's it, guys. We have successfully modulated and demodulated a signal using AM. By modulating the carrier with the message signal and then using an envelope detector to demodulate it, we have shown how AM works in simple way. Thanks for watching, and don't forget to like, share, subscribe. This will be beneficial for us.